The last of my students is presenting from this bioinformatics and genomics class, and Shelby has a problem putting things on a small poster. She just wants to put all the information, and it's such a big story that she's been able to put together from doing this work. I'm really proud of her. She's had, I think, every class I've ever taught, and she grasped this information really fast. I was really impressed with her, and I'm pleased with what she's been able to put together. So I'll let Shelby introduce the material.
Anyways, my name is Shelby Harris, and I'm a senior here. I'm here to present to you my work on the role of the SLC6A1 gene, the variant of 46A1CR, the Myoclonic-Atonic Epilepsy, and Epilepsy and Autism. And as you see, I have a gigantic poster. But I wanted y'all to be, because I knew there was some people in the back, and I wanted y'all to be able to clearly see the graphs to really get how you can understand this, because it would be really hard to grasp it without being able to see the graphs. So starting off, so SL6A1 is a protein, well, it's the gene that encodes for a protein that is a GABA receptor. So a GABA is an inhibitory receptor found in your brain, your spinal cord, and stuff like that. That when the neuron fires, it comes back and inhibits that so the neuron can reset. So you can fire it off again, so you can have motor control and speech and everything. It's very important. But the problem that people have with this is that they lose that effect to retake up GABA. And when you can't retake up GABA, it just stays out in the synapses, like the space between the neurons, and it just causes neurons to fire because it can't be stopped. And that has roles in anxiety, schizophrenic, and epilepsy, because obviously if your nerves are firing, then you're having seizures, because that's what a seizure is. But this gene in particular, this variant, is underneath an umbrella disease that's called the SL6A1 epileptic encephalopathy. I'm so sorry. Encephalopathy. I was like saying that word over and over in my head, but I couldn't get it. Okay, but anyways, that's like the umbrella disease. So with this disease, there's many different variants that cause this. So this is just one of them, which makes this disease extremely hard to treat because there's so many factors going into all these different variants that are causing it. So far, only 34 cases have been found with this disease. It is extremely rare. And really the only thing that's helped them is some epileptic drugs have helped and some valproic acid has helped treat it. But really there's no treatment for this disease yet. Besides, you can just treat the seizures and hope they don't cause enough damage to give them all these, autistic features. But anyways, so Dr. Prokop, he has worked with us in Alpha and accumulated all his data into one big Excel spreadsheet. He gave us this Excel spreadsheet to do this work on here. So I have made all these graphs on my variant, and I chose my variant because it has a really big change in amino acids. It changes from the cysteine to the arginine, and the cysteine, as you can see, is very, very small. It has a sulfur group that's nonpolar, versus this arginine right here is very, very large and has 3 whole nitrogen groups, which are positively charged polar molecules, which is a huge difference, and that definitely causes some problems. This is also a highly conserved protein area. This protein is very conserved, and if you have a mutation in this area, these proteins tend to be very, very detrimental to your health. So I was like, well, I want to choose that one because it's bad, and it will make for a good project. But anyways, using that Excel sheet and that data that we got from Dr. Prokop, I was able to do Excel sheet graphs with some stats. And so right here in figure 1, I have the amino acid impact over amino acid number. And the impact is just how likely it is to be a detrimental mutation, how likely it is bad. And you can see here we have a known pathogenic patient graphed along with my variant. So my variant is high in impact, and it's really close to the patient, so that gives us another thumbs up that it's probably a bad variant. It's probably causing these problems. In figure 2, we now have a box Lister plot with our clinical significance. So here we have this orange is benign, this gray is likely pathogenic, and this yellow is the pathogenic variants. And then here is our known patient who has the disease, and here is my variant. So my variant sits very, very top, the top 5% of benign, so it's very unlikely that it is just benign. But it sits really comfortable in the pathogenic and the likely pathogenic boxes, which statistically tells us this is possibly a pathogenic variant. And then down here I have another box of Worcester blot over the amino acid carbon alpha RMCF. So RMCF just tells us how similar two proteins are. It's bound by NR, just some chemistry that was done there. And it just tells us that these two proteins right here, my patient and my variant, are very, very similar, just in their chemical physiology. So if we're very, very similar to a known pathogenic variant, then we're also probably pathogenic ourselves. And then here we have figure 4, which is the final graph about the codon conservation. So essentially, 21 codon conservation is we took 10 codons down and 10 codons up and ours. So we got 21 codons, and we essentially found how conserved are these codons here. And if we had a really, really high conservation score, like these peaks right here, that means that we are highly conserved. If we had low peaks, that means that we are not conserved. And like I said before, if we have a mutation happening in a conserved protein, then it is likely pathogenic in nature. Versus if it was non-conserved, because conserved proteins are revolutionary important, that's why we kept them. So here is our pathogenic patient right here, is very, very conserved. And then here is my variant right here, which is less conserved, but still very, very high in the peak. So this is still a highly conserved protein, which tells us that this is a very, very important protein, and it is not having a mutation in this very important protein is most likely going to cause some problems in the long run. And so that's our quantitative data, that's our number, that's our stats. It told us that yes, this is probably very, very likely pathogenic, so that checked out. So then we moved on to our SARA modeling. So this is protein modeling using a computer. And this is the first time this gene had been modeled using your SARA. And this is our qualitative data, which just means we can just look at it and say, yeah, that's probably going to cause some problems. Because if you can look here in this protein, we have it colored in black and white. Right here, this red, if you can see it, is our gene itself. And you notice it's on an alpha helix that's pointing to the inside of the channel. And the fact that it's pointing to the inside of the channel means that it's directly interacting with the GABA as it comes down through that channel. And since that's happening, since I told you before that this is going from a very, very small molecule to a very, very big molecule, it's most likely blocking the GABA as it comes through. So it's essentially like if we have a circle, we have a circle hole to fit our circle in. But now we have a circle, and now we have a star-shaped hole, and it's not fitting because this is sticking out to here, and it's not probably only physically blocking it, but it's probably also, there's probably some chemical reactions going on right here that it doesn't like, and it's not allowing the GABA to pass through and to set that neuron like we should. So that's our protein itself. This is the protein inside its cell membrane, and this arrow right here is pointing to my gene, so you can be able to see it because there's a lot of color going on right there. But this is extremely cool because then once we put it into the membrane, I noticed that it's actually very, very close to the membrane. So it's still pointing inside the channel, but if this is the membrane that's pointing like that, it's still kind of close to it. So I'm wondering now if that will maybe affect the phospholipid graft in the cell membrane. And phospholipid graft is essentially where proteins can tell the phospholipids within the cell to know where to position themselves so they can best undergo their reactions. So it's not all throughout random scattered in the cell, they go to the same area. So I'm saying that might also cause some problems and that might be moving around. And we might have some issues with that. But that's it, it's so great. That's extremely cool. This is the first time it's been done. And I was really excited to see that. So anyways, in conclusion, our quantitative, our stats checked out really well. This is following the pathogenic patient. It has high impact. It's fitting into our line likely pathogenic box and whisker plots. It's highly conserved. It is most likely going to be pathogenic in nature, just from our numbers. And then also from just looking at that, we can say, as a biologist, I can say that's probably going to cause some problems. That's probably going to cause some problems, just from looking at it. And since this is extremely rare, I was only able to find one resource on it online in the ClinVar database, and they essentially said it was this genetic testing company in San Francisco. They were essentially like, we have no idea how important this is, but these two amino acids are extremely different, and that is definitely going to cause some change there. So they agreed with us that this is probably a pathogenic you know, you're just from looking at it. And some work has been done on this, but future studies, we're going to start looking at novel drug ligand estimation. So seeing this simulation computer, we can make artificial synthetic drugs and have this and run it through, and then we can test to see how well that would work. So versus the old method of you have a patient with this disease, you would give them a drug and you would wait, and they would either react or not react to it. They might even react very bad to it and get worse. So this will cut out the middleman of we don't have to worry about those reactions happening. We don't have to worry about pushing drugs into people and waiting and losing time. So it will save time, it will save money, it will save just patient comfort. GABA ligand reactions, what is happening with the GABA? Can we somehow make GABA go through this? Can we get GABA around this amino acid and save it to go in to reset it? Possible future variants, compare variants between these two, see similarities. Other molecular protein reactions, there's so many possibilities that we could do with this modeling. It's just amazing. And some studies have gone into gene editing. Since it's just a single protein mutation, gene editing is probably a really good way of doing this. And if you're interested in that, you can look up the SLC6A1 Connect, and they're doing a lot of research at UT Southwestern, a lot of great research there, if you're interested in it. That's it. So any questions?
I have a question. The more work that you've got a lot of things that can be done. What would you see yourself doing next to further this research?
I would really like to do more of the simulations, and I really like the drug simulations, just because that would be extremely cool just to set up a series of things and just watch them run through. I think that would be extremely helpful. It would save a lot of time, and it would give us, you know, we can cut out, this drug is not good, this drug will probably be good, and it will cut out, say, if there's any, like, offstream effects, so we can say if it runs through this protein, but let's say it affects something else, we can maybe see that through our simulations too. And that's what I would personally like to pursue.
You mentioned that the gene is highly conserved. How broad is that sampling? Is it across primates or other groups?
It is extremely conserved among animals. We did look at a graph. I didn't include it in here, but this is a highly conserved gene happening amongst many different animals. Yes.
I feel like this is one of those things that your grandchildren are can't believe it was ever done any other way. Like what, you just gave people drugs and waited to see what happened. But like, what kind of timetable do you see for this just becoming the norm?
This is very, very new. Bioinformatics is extremely new, but it's also going extremely fast. A lot of people are interested in this. I definitely see within the next 10 years just being very common. I'm seeing gene editing. I'm really into gene editing. I'm seeing that becoming extremely common in 10 years. This bioinformatics, all this computer stuff is going to go so fast that in 10 years we're not going to believe what's happening. I mean, like, when I'm finished with my graduate school and everything, when I'm, now a real scientist and stuff like that, it's going to be so different from when I'm standing right here. I'm going to be like, oh my God, I can't remember. Like that used to be like just like a thought up in my head. Now like undergrads do it. So I'm extremely excited for this. I think it's going to be extremely well.
Lastly, I'd like to say you're a scientist already.
Yes.
Yes.
I agree. Thank you.
All right, let's thank our speaker.